Welcome to The Explainer. I'm absolutely thrilled you're here today because we are taking a really fascinating journey. We're going to do what I like to call a micro to macro zoom. Basically, we'll start by looking at the invisible, microscopic particles that make up, well, absolutely everything around us. And then, we'll zoom all the way out to see how the behavior of those tiny, jittery little particles dictates massive, real-world phenomena. By the end of this, you'll see how heat literally shapes our universe, from the weather right outside your window to the engineering of a massive cross-country railway.
But before we get into the heavy physics, I want to hook you with an everyday mystery. Why can fish survive in a frozen pond? Think about it. It's something we see all the time in winter, a lake completely iced over, solid crust on top. Yet beneath that freezing layer, an entire ecosystem just keeps swimming along like it's no big deal. How does that work? Why doesn't the pond just freeze from the bottom up and trap everything inside like a giant ice cube? Keep that question in the back of your mind. We're going to reveal the highly surprising and honestly incredibly fortunate physics behind this a little later on.
All right, here's our roadmap for today. We've got 6 foundational steps. First, the kinetic particle model. Second, gas laws and temperature. Third, the physics of expansion. Fourth, specific heat capacity. Fifth, changing states of matter. And finally, transferring thermal energy. It's a straight shot from the invisible atom right up to large-scale engineering. Let's get into it.
Starting off with Section 1, the kinetic particle model.
Okay, let's dive into this. To really understand heat, we first have to establish the absolute baseline rule of all matter. Everything is made of particles, and those particles are always moving. Always. Now, we obviously can't see them with our naked eye, but scientific eyes, like powerful electron microscopes, prove they're very real. These tiny building blocks are in continuous motion. They vibrate, they bounce, they collide into each other constantly. And this continuous, jittery movement, that is the foundation of what we physically feel as temperature.
Notice how this movement completely changes across the 3 states of matter. In solids, the particles are locked in this fixed, regular pattern. They can't move around freely. They're just vibrating in place, held tight by strong attractive forces. But if you add heat, you're essentially giving them a massive energy boost. Those particles vibrate harder and faster until, bam, they break out of that rigid pattern. Now you've got a liquid, where particles are still close but can slide randomly over one another. Add even more heat, they break free entirely and become a gas. In a gas, these particles are spaced incredibly far apart and just zip around at insane speeds. To put that into perspective, the air molecules around you right now are dashing around at roughly 500 meters per second.
And that high-speed movement sets us up perfectly for Section 2, gas laws and temperature.
So we just saw how chaotic this microscopic particle movement is. If heating a substance means we're speeding its particles up, then logically cooling it down means we're slowing them down, right? So what happens if we just keep cooling it? Eventually, you're going to hit a universal limit. This is called absolute zero. It's the temperature where all particle motion literally ceases. The substance has absolutely zero internal kinetic energy. You simply can't get any colder than this because, well, you can't have less than zero movement.
So, where does this happen? That ultimate freezing point occurs at exactly minus 273 degrees Celsius. Scientists actually created the Kelvin temperature scale starting right at this point. So, minus 273 degrees Celsius is 0 Kelvin. And some really strange things happen near absolute zero. Certain liquid metals will actually flow without any friction, and some materials become superconductors that can conduct electricity perfectly, forever. It is literally the absolute bottom of the temperature universe.
Now let's look at how these moving particles behave when they're trapped in a container. This is governed by 3 fundamental gas laws. Think about pumping up a bicycle tire. When you press down on that pump, you're cutting the volume of the gas's space in half. Because those particles are now packed into half the space, they're going to hit the walls of the pump twice as often. That's Boyle's line action. Halve the volume, double the pressure. Or think about the pressure law. If you take a closed can of gas and heat it up, those particles move way faster, they hit the walls harder, and they hit them more frequently. That drives the pressure up. These neat mathematical equations we use in physics, they are purely the result of billions and billions of microscopic collisions.
Let's move into the observable world of engineering and nature with Section 3, the physics of expansion.
And this brilliantly illustrates what happens when we scale things up. Because particles vibrate more violently and push further apart when they get heated, almost all matter expands when it gets hot and contracts when it cools. Take railway tracks, for instance. To stop them from completely buckling under the massive forces of summer heat expansion, engineers create these tapered, overlapping joints. It gives the expanding metal room to slide without warping the track. But water does something incredibly weird. Unlike almost every other substance in the universe, when water cools down and freezes into ice, it actually expands. The particles arrange themselves into a crystal structure that takes up way more volume. This easily generates enough force to burst metal pipes or shatter a glass bottle of milk left out in the cold.
Which brings us right back to our intro question. Why do fish survive in a frozen pond? It's because of water's weird, anomalous expansion. Water is actually densest and therefore heaviest at exactly 4 degrees Celsius. So when winter rolls in, the water cools to 4 degrees and sinks straight to the bottom. As the water gets even colder than that, 3 degrees, 2 degrees, 1 degree, it actually becomes less dense, so it floats up near the surface. Finally, it hits 0 degrees and freezes, expanding to form ice. That ice stays floating right at the top, acting like a perfect insulating blanket for the pond. The fish get to stay safely down below in liquid 4-degree water. It is a miraculous quirk of physics that literally makes aquatic life on Earth possible.
Shifting gears just a bit, let's look at Section 4, specific heat capacity.
You know, not all materials heat up the same way. If you leave a metal spoon and a block of wood out in the hot sun, the metal gets absolutely scorching while the wood barely warms up at all. This is because different materials require wildly different amounts of thermal energy just to raise their temperature. For example, it takes 4,200 joules of energy to heat 1 kilogram of water by just 1 degree Celsius, but it only takes 800 joules to heat the same amount of soil. Water needs more than 5 times the energy just to heat up. This perfectly explains why island climates, which are surrounded by oceans, are so incredibly stable. The ocean is a massive thermal buffer. It absorbs vast amounts of the sun's energy all summer long without its temperature rising very much, and then slowly releases that heat during the winter. Water is effectively nature's ultimate temperature regulator.
Let's push past these temperature limits in Section 5, changing states of matter.
So, when you add enough heat to a liquid, it boils into a gas, like the steam you see rising from a kettle. But here is the really fascinating part. If you stick a thermometer into boiling water, it will read 100 degrees Celsius, and it will not go 1 degree higher. I don't care how much heat you keep pumping into that kettle, the temperature just flatlines. Why? Because of something called latent heat. At 100 degrees, the heat energy stops raising the kinetic speed of the particles. Instead, that energy is going entirely toward tearing the particles apart. It's overcoming their attractive bonds to force the liquid to turn into a gas. The heat is basically hidden, which is exactly what the word latent means, inside the state change itself. Now, state changes don't just happen at the boiling point. They can happen below it too, through evaporation, which acts as a seriously powerful cooling mechanism. Let's walk through the microscopic steps here. Even in a lukewarm puddle, particles are moving at a bunch of different speeds. The absolute fastest, most energetic particles right near the surface have enough energy to break free and become a gas. Because the highest energy particles have literally left the building, the average kinetic energy of the particles left behind is now lower. And as we know, lower kinetic energy means a lower temperature. This exact microscopic physics is how the human body cools itself down. When you sweat, the most energetic particles of water evaporate right off your skin, taking that thermal energy away with them, and leaving you feeling cooler.
And that brings us to our final section, Section 6, Transferring Thermal Energy.
Now, what's really interesting about this slide is the dramatic difference between conductors and insulators. We know heat is microscopic movement, right? But how does that movement travel from a hot object over to a cold one? In solids, the main way is conduction. In insulators like wood or plastic, heat travels super slowly. One vibrating particle bumps its neighbor, which bumps its neighbor, passing the heat along kind of like a slow game of telephone. But metals are fantastic conductors. Why? Because metals have a sea of what we call free electrons. These tiny delocalized electrons aren't tied down to any single atom. So when they get heated, they zip rapidly through the metal structure, carrying that thermal energy from the hot end to the cold end almost instantly. That is exactly why a metal spoon gets incredibly hot in your cup of tea, but a wooden spoon stays perfectly safe to touch.
Which brings us to a really fun final thought. Next time you walk up to a metal door handle in the middle of winter and it feels freezing to the touch, pause for a second and ask yourself, is the metal actually colder than the wood of the door? Actually, no. Usually they are at the exact same room temperature. The metal just feels cold to you because it is a brilliant thermal conductor. It is violently and rapidly stealing the thermal energy right out of your hand. I really hope this explainer has totally changed the way you look at temperature, heat, and all those invisible dancing particles that make up our universe. From the crazy physics of a frozen pond to the sweat cooling your skin, it's all just energy in motion. Thanks so much for watching, and keep questioning the world around you.